All right, everyone. This is going to be our video on how to use the DIC analysis software in order to calculate Poisson's ratio for the lab. So I've added a link to a software program to the lab in LoudCloud that's called UFreckles, and the freckles are for the pattern that we put on there. Down here is a Windows installer that we can use to do that. So if you click this, it'll take you to a link here where you can download this installer. Apparently this is a French site because this is translated from French. So click this, download it, install it. Again, you can find the link in LoudCloud, just in the lab description. And then you should get a program here called UFreckles. And I'm going to go ahead and open it. And I'm going to show you how to do it. It's actually not too hard to use. There's some features that I kind of miss from GOM Correlate, but overall it's plenty good enough. So here's the program. This is what we're going to do. It's got lots of, this can actually do a full 3D. It's really it's actually got more features in it than I know what they do right now. Maybe I'll get to explore this some more, but it's very powerful software. But what we need to do is pretty simple. So we're going to go to this first part right here. I wonder if there's a way I can even I don't know if I can make this bigger. But this first one right here, the tooltip says start a new DIC analysis. So that's what I do. It's this very first black freckled thing. So we click this and it's going to bring up a window asking us to select our images. I do wish some of this stuff was a little bit better documented, but that's right here. So I have my flash drive plugged in, so someone left me all their nice data here. So we'll go ahead and grab all their yellow data. I can just select all these pictures. Right, select all these pictures and I just click open. And it brings to the pictures, and it's got these arrows up here where I can click through the pictures just like before. You can see someone moving in the background. You can also skip around. You can go 1/10 of the total number of frames to skip through quicker if you want. But anyway, that's that. So the first thing we need to do is we're gonna right click out here outside of the picture, and we're going to pick the NURBS model. It's a not going to explain it. It's we're not going to want to use these two. We could use either this one. This one's slightly better. It's just different ways of connecting up the different parts of the image together. So I've played around with it a little bit. I think NURBS is the best. And then it starts trying to define a grid, and this is not at all what we want. So we're going to right click somewhere on these blue lines, and we're going to change our again, there's lots of options we can make. We're going to define our zone to be a rectangle, and then we just click the two edges. I would start at the bottom and go not quite all the way up, not even close to all the way up, really. The problem is this stretches so far that by the end of this is going to go off the screen, or at least some of it might go off the screen. So we don't want to pick the whole thing because then we'll lose a lot. We're just going to pick a little bit down here. Now, one of the things that you can do is if I pick the element size, then I can scroll wheel down and click 20. So now you can see the squares are smaller. I think for this data, 20 worked pretty well for me instead of 23. The trade-off is the smaller the grid, there's more likely that you get errors because there's less pixels to calculate by, but you get better resolution in your data. So I think 20 is about good for this pattern. And as you can see, if you look, each square is very unique, which is kind of the whole point of the pattern. So this pattern looks really good on this one. So I'm not sure who did this, but great job here. All right. So now that I've defined my zone, all I need to do is click save. And it's going to save the parameters of this test in a data file .dat. So we just save it. This is a step that seems like it could be automated, but it is open source software. So and now we click this one that next to this here that says run job, right? And it comes up with this thing. And then here we click again, open, and we pick this parameters that we just saved. And then we click run. So again, it's the first thing we do is click the save button, and we save the parameters for that test. You can pick any name you want. Then we have to load those parameters back and click run. Again, a little bit silly, but I think that's just how the code works. Eventually it'll say end running test. We can close this, and now we click this open data, and now we have these two result files. We don't want the error one, we just want the test .result file, and we open it, and now it skips to the as you can see, this is the last image, and our rectangle gets gone off the screen. So let's go back to the first one. So this still shows the grid because it's the reference, and as we click through, now we've got pretty colors. This here is now displacement, is what it defaults to showing. We want to see strain. So come down here to where it says these steps. I right click and I can do strain. And looking at the coordinate system over here, the longitudinal strain is the strain in the y direction. So I do EYY, and I can see how that strain changes. Now it is changing the scale each time. So what I also like to do is to come here and go to color scale and switch off auto adjust and go to the overall min max. So now if you go to the end and come back to the beginning, you can see our overall strain is between basically 0 and 60. And so the color is just going to start changing more and more red as it goes up. I like that better. I think it makes more intuitive sense to think about it that way, as the strain is just increasing. And so it's the lowest it can possibly be here in the blue and moves up. And we could do the same thing if we want to see it. We can change our strain to strain in the X direction. So this one we would expect would be negative because it's shrinking. I'm going to do the same thing, change the scale to overall min max, and then go to the end and back to the beginning. So our maximum is negative 0.3, our minimum is minus 0.5. Okay, so it needs to go all the way to the end to get that overall min. And then now, okay. So for some reason, it only does the overall min. When you do overall min max, it does the biggest one it's seen so far. So you kind of got to skip to the end and skip back to the beginning, and then your scale bar will be the overall. So you can see here we're near at the maximum, and as we stretch farther, that strain gets more and more negative as we go down, which is what we expect. So the question is, how do I get Poisson's ratio information from this? So I actually need the graphs are cool and they're very fun to look at, but I need some actual numbers. So if I right click on here, I can do post processing, and I think the easiest way to do this is plot over a line. So I'm just going to draw a line kind of in the middle of this rectangle. And this is going to give me epsilon x and epsilon y, and as I click through it, it's going to show them as plots. Now this plot, they are going to keep changing the scale, and I don't think there's any way to lock this scale that I can tell anyway. Again, this and then to get an actual number is to click this point here, and so I picked maybe pixel 40, and it's going to give me the y value at each of these ones. So if I go back to the beginning, and the strain's 0 on the reference image, basically I can go through and I could copy these down: 0.0238, 0.04815, 0.07, 0.1, 0.12, 0.15, and copy down a certain number of these. Oh, this is not moving anymore. You can still have it move if you want. This is this deformed image. You can choose whether you want it to, whether you want to see the image deformed as you move it or not. It doesn't really matter. But basically copy these down and then do the same thing for so I pick a same X value and I can copy down these strains as well. go back to the beginning, negative 0.005238. And basically what I would do is I would copy down these strains, and then I would find a Poisson's ratio for each of them. So you do the negative lateral over the axial, and then I would probably just average out those Poisson's ratios, so that you get a nice, just the best, your best possible values to average across all of those. So we're actually ended up only taking the strain at basically one point, the midpoint of this line. But including a picture or two of the strain fields might be interesting as well. Plus, it's fun to play around with and look at it. So that's how we use this DIC software. This will get posted to YouTube as soon as I can post-process it, though it's already done if you're watching this. If there's any questions, hit me up on Discord. And great. Hope this helps.